Okay, good evening, everyone. Can you guys hear me? Could you type something to the chat? Thank you, thank you. Okay, good. So we are in the 12th week, I assume. We got a couple more weeks to go. And so today my goal is to really go over a few things. Actually, hold on 1 second here. That's for the next time. But today my goal is to go through once again, remind us about DFS and BFS and the algorithm, the pseudocode, and the analysis. And we'll talk about topological sort using DFS. That's the last thing we did. And also some examples, and also a new way of doing topological sort using BFS and the analysis. I think this algorithm you probably would be needed for the next assignment. Some component of this algorithm. The next assignment is already on AutoLab, and you can, I think it's due May 1st, so there's a couple of more weeks to go. But you may want to get started as soon as you want to, you can, right? So we'll say a few things about the graph implementations. I mean, there are many ways to do this, and this is one way that that this course has done in the past, but different courses, if you're looking at other code that I have posted, they might have a different way of implementing it. So one way to implement a graph is to think about a notion called a neighbor. So we have this neighbor idea. And inside the neighbor, you have some vertex number. Let's say 20 is the vertex number. And then you have the next, which is pointing to another neighbor. So essentially, we are describing a linked list. So we have, if you have an object called a neighbor, we can have a linked list that describe these things, right? And then a vertex can be defined. Again, there are a lot of different ways to do this, so I'm just showing you one way. So a vertex object will have some name, which is a string, and then you'll have an adjacency list, which is a neighbor. Okay, so this is a neighbor. And the neighbor is the same format as what you saw there. So essentially, where we're describing that each vertex has some level of an adjacency list, which describe the vertex, if this is vertex I, and then it's connected to J. There's a link from I to J. Okay, that's what it describes. And then you can define a graph, and that's so on. Okay, so excuse me. So that's sort of a somewhat of an implementation detail. You might need that or something similar to that. You don't have to do the same thing, but you might need something similar to this in the implementation of the next assignment that's due on May 1st. All right. Any questions on this? You can type it into the chat. All right. So let's move on to. You can always type something in. I will respond to it as soon as I find some time. Okay. So one of the algorithms, so graph traversals, there are two major algorithms. One's called the BFS, which is the breadth first search. And the idea of the breadth first search is that you start from a node, and let's say I mark 0 at that node. What that means is that the distance from that node to that node is 0. But then if I take the adjacent ones to that, which I can find by using the adjacency list, and I can write 1 for their distance. And then if I take a node with distance 2 or distance 1, if I take the adjacency nodes from there, I can write 2, because that would be the distance from the original node. So essentially, I'm trying to find the distance from the original node. And same way we can have sort of like breadth first search is essentially traversing by the levels. So we have level 2 nodes are going to be EBCH. So these are level 2 nodes, and this is the only level 3 node. So the this 3 essentially so the idea here is that you're finding this is also called the level order traversal, right? So this is called the level order traversal. Okay, the way to implement the level order traversal is that we do start with a node, some node U. Let's say we start with node G. So we enqueue node G in a queue. So we have a queue here. Okay, and while the queue is not empty and G is not empty, we're going to dequeue this node and process that node, and then take all the adjacency elements to that node. So for example, who are the adjacent elements to the node G? They're going to be A and D. So we're going to enqueue all the adjacency elements to the node G. That we can find because we have an adjacency list representation. Essentially, there's an edge from G to D and G to A. Okay, so we can find those two things. And then we go back to the while loop and then take the first one in the queue, A, and then enqueue all the nodes that are adjacent to it. In this case, they're going to be E and B. So we will put the nodes adjacent to it. And then we do the same thing. Again, we go back and get the next one and put the nodes adjacent to D. That's going to be H and C. And then take E, process it. And E has no, well, A has the adjacency element B, but B is already in the thing. So we're not going to put anything into the list. And then we process B. And B has the adjacent element F, so we put the F into that. And then we take H, we process H. We look at adjacency element of H. Those are D and C, but both of them have been either processed or in the queue, and therefore we don't do anything.
Mm-hmm. Okay.
And then, hello? I think I heard someone talking. Let me just make sure that everyone is muted. Yes, okay. Just to, sorry about that. Yeah, that's okay, no problem. Okay, so, and then you process, you take something out of the queue, which is C, and then process it and print it out. And then the final one is F, so the queue is empty. Now, if you number these things in the order that we looked at, notice that these are all 2 numbers, and this is the 3 number. So the BFS, essentially, this simple algorithm gives you the correct order of traversal. How you traverse nodes within a single level is determined by the order in the adjacency list. Okay, that's how you will do. Okay, so let me take a look at the questions you have asked. Okay, the first question is, was the pen-based computing project for a Rutgers class? The answer is no. I'm new at Rutgers. That was a seminar I offered at Princeton. It's a very actually that was a program I offered at Carnegie, and I apologize for that. And I think I will show you you can watch the video. It's very interesting program. I will demonstrate that to you. In fact, I'll send you download information. Okay. Why is it q.nqu in the for loop? Q.nq in the for loop. Okay, so in this case, what we are doing is we are taking a node and then we are finding a node. So we are dequeuing a single node V, and then we are taking all the things adjacent to V. Let's call them W, and then we put, okay, this should be W, I'm sorry. So, okay, thank you for asking that question because that should be W. So we are essentially enqueuing all the things adjacent to that node that we just dequeued into the queue, back into the queue. Is there a post-order pre-order traversal? No, I think the DFS kind of deal with, you can say, if you do DFS, we can talk about pre-order traversal. That means you process the node as soon as you see it. Or post-order traversal, that is, if you process the node on the way back. Okay, so that was used for a topological sort, for example. Okay. The other course, does it determine what is in each level by adjacency list? Yeah. So I think the adjacency list is used here in this case because you need the adjacency list to get all the nodes that are adjacent to V, and then you process. So that's how you get it, right? And okay, good questions. Yeah, thank you for asking that. So let's do runtime analysis of BFS. Okay, we want to do runtime analysis of BFS, right? So if you look at this BFS, there's two loops. So there's a loop here, and there's a loop here, right? And the first loop will run how long it's going to run. If you assume that the number of vertices is n and the number of edges is e. So while q not empty, how long it's going to run? Yeah, so that's correct. So it's going to run n times because we are processing each node exactly once. Okay, so it's going to be big O of n. If you look at this, right, and that's a for loop, and it says that for W in adjacency Q and Q. So you're running, like, for example, each of these for loops run inside the big loop. But there's an interesting observation you have to make here. Now, each of these, how many times this loop runs, that loop, what is the exact time that loop runs? Like if you just take that loop, right? You take for W in Q adjacency V. So it's sort of like this, okay? So we have this adjacency list to V, and these are the W's, right? So these are the W's. So we are processing these W's in that loop. So how many W's are here to process? Okay, so someone wrote degree of V, which is kind of okay, but not exactly, right? I think I want you to be more specific about that. I think if I just take one loop, right? I want the answer in terms of V, just like you said, degree of V. V dot length. Yeah, so you could say V dot length. Another way to think about this is, let's see, I'm going to wait for out degree. Yes, I think I like the out degree. So out degree of V is what it is, okay? So although you're going through every node, this is a place where you don't multiply these two, right? Because when you see two loops, you tend to multiply. Out degree is the number of nodes, number of edges that are going out of a specific node. That's the out degree. That's the definition. So if you look at this, every edge is touched only once. Okay, although this big loop kind of runs throughout, So essentially, these loops here will run the sum of the out degrees of V. Okay, so they will run sum of the out degree of V, or the V's are all the nodes. Okay, but really the total out degrees of V is E. All right, so if you say the answer is n plus E, you're correct. But you don't want to do multiplication or anything. You want to just make sure that you understand what the code is doing. All right, any questions there? So this is BFS and the analysis of it in a way, right? Okay, let's go do some questions here. Okay, I want to take just a little break. So let's take break in the sense that let me run a poll here. Okay, see if you can find the answer to that. Okay, good. I think everyone is sort of getting this. It's the answer is number 7, right? Because if you have 6 edges, each edge is responsible for two two connections. But so if you have 6 edges, the maximum would be something like this: 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So seven nodes. But you could have 7 edges. I mean 6 edges with a small number of nodes, right? So you can have 7 edges with what is the minimum? If I change this to minimum, what is the minimum number of nodes in? Let's just type it into a chat here. What's the minimum number of nodes? Let's see if you can with 6 edges. I want 6 edges, but minimum number of nodes. Oh yeah. I think right. So I'm assuming this graph is connected, right? So someone said 4. Let's see whether we can do it into 4. 1, 2, 3, 4, 5, 6. Right? Can I do 7 with just 4? Okay. So 4 nodes. What am I missing? I think I have 6 nodes, 6 edges. Okay, I'm sorry. Yeah, 6 edges. Okay, good. So 4 is the right answer. Okay. So that's sort of clear, right? Let's do another question here. Let me open up a poll here. Okay, so looks like n minus 1 is winning. Yeah, if you have n nodes, you can have minimum number of edges would be n minus 1. Okay, because that would be the sort of like a tree kind of thing that you can work with. Okay. Okay. So let's do one more here. Let me open up the poll again. Okay, let me publish the result. So it looks like everyone is kind of thinking about this. So right now this is 28% and 26% responses and 22% responses. Okay, notice if you say the best one, it's the DFS. Okay, because DFS will get you from one node to another, find it. But it's not, I mean, you can also use BFS to find the distance from one node to another, like we saw in the example that I showed you there. So if you say either one, that's still okay. You just say BFS, it's okay. But if you say the best one, it's got to be DFS. Okay, so the best one is a DFS. So let me see whether I have any question in the chat here. Okay, great. All right. Okay, so we talked about the BFS. Okay, and the DFS. Let's go to DFS. So the DFS algorithm. So again, this is one implementation of the DFS algorithm. Notice that it's implemented recursively. Okay. So this DFS algorithm, you take a starting node, which is V. Always the DFS has to start from somewhere in some node. And then you're also maintaining a global array called visited, which is an array of Boolean. So if a node is visited, you don't want to go there again, so you change that index to true. So because you're starting from the index V or vertex V, but in visited V is true. So you start with that mark true. So I've already been there. Then you get the adjacency list of V. Okay, and then you run it through a for loop. And if it's not visited, then you try to visit that number, right? So basically, this is sort of a very simple recursive algorithm that keeps going. So it's starting from here, keep going, doing DFS until it finds a dead node. Okay, once it finds a dead node, it'll try to come back and maybe go in different directions. Okay, so and find another dead node. So in this way, you will find all the paths from node to a. So this will guarantee that if you start from some vertex V, and if V is connected to U, some other vertex U, it will find a path from V to U. Okay. Now, We say reachable nodes. DFS and BFS traverse to all reachable nodes. Reachable means that there's a path from node V to node U. Okay, if a graph is not strongly connected means that there's a path. So this means that there exists a path from U to V for all U and V. So this symbol indicates that they exist. They exist. A path from U to V for all U and V. Okay. And sometimes if the graph is broken, let's say you have a graph like this, and then you may have a graph. The graph is not connected like this one here. So this graph has maybe two components. So if you do BFS from one component, you can reach all the connected components. So depending on where you start, if you start from here, you won't be able to reach all the components. But if you start from here, you will be able to reach all the components. And then once you finish that, recognizing that you didn't process all the nodes in the graph, you can start from another node that was not considered and then see if you can reach the other nodes. In other words, when you do DFS, you will have to make sure that all the nodes are touched through your traversal. You might not be able to do that in one iteration because you may have a small connected component that will where you have to go to because if it's just connected, you have to find another starting point. Okay. So there are a lot of interesting graph questions you can ask. Okay. I mean, graphs are really, really important. Like, for example, if you take the Facebook graph, right? Facebook graph. What is the size of N in your mind, and what's the size of E in your mind? Okay, it says the N is the number of users, E is the number of friends, the number of edges, right? So the edge is a friendship. Okay, is Facebook directed or undirected? Facebook is undirected because that means if A is a friend of B, and B is also a friend of A. Okay, so here's my estimation. I can only guess, do an intelligent guess. I think the Facebook has, if I'm right, has about 2 billion users. So Facebook has about 2 billion users. Anyone know the right answer for Facebook? And 3 billion, I wrote 3 billion. Is that too much or too little? Facebook is undirected. Does anyone know how many people use Facebook? I mean, how many people have accounts, not use Facebook, right? 2.45. Okay, I'm pretty close. Okay, so it's 3 billion, right? Now, how do I estimate the number of edges in this graph of 3 billion? All right. So let's assume one of you guys can type. How many friends do you have? Just type few numbers. I'll pick one. Okay, someone has 0. 514, 0. Okay. All right, so it kind of varies. 115. All right. I have about 10 friends. I started a Facebook account in 2006. Okay, 350, 30,000. No, that's not. I think 30,000 sounds really weird. because you couldn't have that many friends, right? And but let's assume, okay, let's assume for a moment that each person has 60 friends. Okay, 60 friends. Each person has 60 friends on average. Maybe it might be small, but it might be big. But let's make it 100. Okay, 100 friends. So each person has 100 friends. So how many edges you think the Facebook will have now with this estimation? I still have to write something here. I have to multiply this by something. So if you think like this, if you take yourself, you have 100 links going from you, right? And so because there are, so for each person, let's assume that 100 friends, which seems big, right? If you multiply this by 3 times 10 to the 9, that means there are n vertices. So you take 10 to the power 2 times 3 times 10 to the 9, but we have to divide this by 2 because we divide this by 2 because we counted the things twice, right? Because we counted things double because A to B and B to A are the same. So therefore, we are going to claim that the number of connections in Facebook is about 1.5 times 10 to the power 11, which is huge. Okay, that's one with 11 zeros. So that's how you come up with the number of connections in Facebook. Now, when you have a graph like Facebook, you ask the question, is Facebook strongly connected? Strongly connected means that you can find a friendship path from one person to the other, right? To any other person in the world. Well, okay, so most likely not, okay, because I mean, they talk about the 8 degree of separation. That means, if I take 2 random people, I can find a friendship, 9 people apart. I may not know anything about that other person in anywhere in the world, but I'll still find it. But I doubt that Facebook is not strongly connected. But it's possible that there are strongly connected subcomponents of Facebook, right? So these components, these clusters exist. These clusters exist, okay? That means if you know people, like for example, you might assume that people at Rutgers kind of are in a clique, right? And people in another universities will be in a clique. You may find some connection between a Rutgers student and Rutgers clique and another clique. Definitely we have that, right? So friendships, you have friends in other universities. So Facebook is not strongly connected. So we can ask that question, if it's not strongly connected, what is the maximum connected component in Facebook? Like, what is the largest group of people who are friends with each other? We can ask that question, not in a we're not talking about friend of a friend. We're talking about they are somehow, yeah, even if you take friend of a friend, that's okay, because then, you have friend of a friend. Friendship is the definition of this connectedness, okay? And then we can have a question like, if you start with a friend and you find you have a friend, and that one has a friend, that one has a friend, and that one has a friend, and eventually that thing leads back to you. And so we call that a cycle. Okay, so in other words, how do we check with a Facebook graph cycles, right? Facebook graph. You definitely have cycles in Facebook. There's no question about that. And then you could ask a question like, if you give me a U and a V, is there a path from U to V? So in the Facebook context, you're asking the question, if you give me 2 random people, can I find a friendship connection through the Facebook graph to get from U to V? And there are other questions that are more mathematical. like, are the two graphs isomorphic? Isomorphic means that they may look different, but in terms of their shape, orientation is the same. Okay, I won't go into a lot of details about that, but in other words, you may have very similar shape of connections. The same number of vertices, same number of edges, same number of sort of shape. In other words, if you relabel one graph, two isomorphic graphs, you can get the other one from that. One of the famous algorithms for finding cycles in a graph is called the tortoise and hare algorithm. I may have mentioned this in the class at some point. Basically, what we do is that, let's suppose that we have a graph like this. And then at some point, this graph becomes a cycle. Like that. So this also is a good algorithm for finding, excuse me, finding that there's a cycle in a graph. So basically what the idea would be that we know this guy is fast, 2 times as fast, and this guy is slow, right? So 1 times, or half a time, I guess. Right, so if you start them in the same place, hare and the tortoise, and in the next jump, hare would be here. Okay, and the tortoise would be here in time 1. So let me write H1, T1 to indicate time 1. This is time 0. And the tortoise will be here in time 2, and the hare will be here in time 2. Okay, and tortoise is going to be here in time 3. Hare will be here in time 3. Okay, and then hare would be here in time 4. And tortoise is here in time 4. And hare is going to be here in time 5. And tortoise is here in time 5. And then hare is going to be here in time 6. And tortoise is here in time 6. And hare is going to be here in time 7. And tortoise is also going to be here in time 7. Okay, so we found that after 7 hops or 7 jumps, tortoise and hare meets. In fact, that is the test for a cycle, because you will guarantee mathematically that these two will meet at some point if you go through these steps. No matter how many nodes are in the cycle, you can prove it. And do you have any questions about that? It's a very, very interesting algorithm for detecting cycles. Yeah, it is efficient. I think the other algorithm for finding cycles is to just do DFS. So that's the other. Yeah, so it's sort of a linear thing. You just go through this many times, and eventually, in a finite number of times, you're going to try to the two people are going to meet. Okay. When you use the algorithm, how to know when to stop? I guess you check the status of tortoise and hare. And 1 second. Okay. Can you guys hear me? Because it looks like I lost my connection. Okay, thank you. Yeah, so there are some mathematical conditions that could, the one question you can ask is eventually like whether they meet or not. I mean, which you can check very easily, right? Because you know the location of the hare, location of the tortoise, and see if they're in the same node. If they're in the same node at a given timestamp, like in this case 7, you're good. Okay. But there could be mathematical properties of the number of things in the number of nodes in the cycle to determine things more mathematically, right? Even without running anything. You could do DFS is the right algorithm because DFS kind of takes you through the graph. Okay, so you want to use DFS for torus algorithm. Okay. So we also talked about the topological sort. I want to say a few more things about that. The topological sort is it's essentially a relabeling of the vertices in an order so that directed edges only go forward. Okay, essentially you try to relabel the nodes 1, 2, 3, 4 in the graph so that you will only have edges going in this manner. Okay, so this is a graph with 4 edges, but it might have looked different before, but now it's fine, right? So what is the necessary condition for topological sort to exist? What can we say about the graph? Okay, so the graph G is a DAG. DAG means directed acyclic graph. Remember, we just looked at these cycle finding algorithms. So figuring out whether a graph has a cycle or not is very important for this topological sort to exist. Okay, so the algorithm, one of the algorithms we discussed was we're going to start with any vertex, and then we find what's called the post order using DFS. We're going to do DFS traversal and find the post order. Now, what we mean by a post order is that when you do recursion, you start from here. Let's say you start from 1, and then you go to 2, then you go to 3, right? And suppose you cannot go beyond 3, so the post order is going to be 3, 2, 1. Okay, pre-order would be 1, 2, 3. Now remember, in the recursive algorithm, we do DFS of V, and then we call DFS of some neighbor W, right? So we just keep calling DFS within DFS. So because of this thing, it'll go all the way to the end before it'll pull back. Okay, so let's do, and yeah, so what we do is in the algorithm, for the DFS algorithm, we're going to find the post order, which is 3, 2, 1 in this case. And then we're going to reverse the post order. Okay. So let's ask the question, what is the complexity of finding a post order of node traverse? In other words, the question here is that what is the complexity of DFS? Okay, so maybe someone will type the complexity of DFS is really the complexity of figuring out the post order, which is correct, V plus E or N plus E. Okay, that's the complexity of that. And then once you find the nodes in the post order, what is the complexity of reversing it? Yeah, so complexity of reversing is n. Okay, so in this case, n is the number of vertices, because you have only n things in your list, and you just have to reverse that list. Okay, like if you have 3, 2, 1, you reverse it, you get 1, 2, 3. That can be done in linear time. Okay, so so we have to make sure that when we find this, we have to perform DFS on all the nodes. What I'm going to do next is that let's take a subgraph of our requirements graph from computer science majors at Rutgers and do a topological sort on this. Okay. So I would like you to start from 211 and then just give me a sequence of post-order traversals. Okay. So think about that a little bit. Maybe write it on a piece of paper. You don't have to essentially type it into the chat, but see if you can do the post-order for this graph. Don't worry about the edges coming into this block I marked. That's like a subgraph, and only care about nodes within that subgraph. I mean, the edges within the subgraph. All right, so let me start doing this while you guys are thinking. So essentially, if I start from 211, I might go to 352. I'm doing DFS. We go to 419. So this will be labeled node number 0. Okay, so I backtrack to 352 because there's no way to go. I'm going to label that as 1. Then I backtrack to 211, but I have more ways to go. So I'll go to 314 next and 440. And this I will label as 2. And then I backtrack to 314. I have a way to, from here, I can go to some other node, 415. So I will label that as 3. So then I backtrack to 314, which I will label that as 4. Now backtrack to 211 again. Follow this link. All right, and I'm not considering this one because that's not a link coming from. So this is not considered. So 214, then from 214, I'll go to 437. So this will be labeled as 5. Backtrack to 214 and go through this link, get to 417, which I will label as 6. Backtrack to 416 and no other way to go, so I'll label that as 7. Backtrack to 214, I will label this as 8. And that's it. So if I draw the labeling, what I have is 419. Okay, so I have 419. Okay, so let me write 419, 352, 440, 415, 415, 314, 314. Then we have, oops, I missed something here, right? What happened to, well, 336. Yeah, I noticed that the 336 is never counted here because I don't have a way to get to 336 from 211. So 336 is not counted here. So it's okay. I didn't miss anything. Okay. So what is it here? 314 is 4 and 5 is 437. 437. And then 6 is 417. 7 is 416. And 8 is 214. Okay, so this is called the post order. All right, and if you want the reverse post order, then you'll have to reverse that, which will give you 214, 416, 417, 437, 314, 415, 440, 352, and 419. Now, so we make a claim that we can only go forward in these links. Okay. So if you have 214, I can go to 416. There's an edge there. From 416, I can go to 417. And 437 is kind of like a node that's, how did I get to 437? Not really sure. Or through 214, right? Okay. And then let's draw the other ones. We have 211 to 314. what happened to 211? I guess I didn't write 211. So 211 is here. So there's 211. Okay. So we can have 211 to links from 211 to 314. This is 314. I apologize. Oh, wait. The fourth one is 314. Oh, 314. 314 here. So 211 to 314 and 211 to 352. To 352 and then 352 to 419, 352 to 419. So notice that when I draw the links, they only go forward. There's a question here. 211 should be the last one. That's right. Okay, so I already added that. Why is 437 after 417? 437 after 417 because when I come to why is 437 after 4? Okay, how did I come to 437? Surely I could come to 437 through this, right? So I came to, yeah, so I took this link to come to 437. So that's why it became 5 and 417 is 6. But the, I mean, there are other things missing here. Okay, so I didn't draw all the connections. But notice that I came from 214 to 437. I could have gone to 416 and then 417. So the order could be different. Okay, so this is not a unique order that I will get by doing this. Okay. All right. So basically, I think that's the idea, and you should practice more on these. Let's see whether we will have enough time at the end to do something. I'm going to put some code examples in the Sakai folder for you guys to see that. Okay, so we'll come back to that. Okay. Well, 1 second here. Okay. So there's also another way to do topological sort using what's called BFS. Okay, what we did here was a DFS, and a topological sort using BFS is essentially the algorithm goes like this. Let's compute all the in degree of vertices. Let's define the in degree of a vertex is the number of nodes. Okay, number of nodes coming into that, coming into V. That's called the in degree. Now, clearly, if you think about a graph like this, okay, let's write the in degrees of these vertices. Let's call them A, B, C, D, E, F. And could you write the in degrees of A, B, C, D, E, F? Number of edges, okay, not the nodes. So let's do the vertex A, B, C, D, E, F. Okay, let's compute the in degree. Right. So in degree of A is that how many edges are coming into V? The answer is 0. Okay, how many edges are coming into B? The answer is 1. How many are coming into C? The answer is 1. Okay, how many are coming into D? The answer is 1. How many are coming into E? The answer is 2. And how many are coming into F? The answer is 1. So clearly, we can find the in degree of, so someone looks like someone correctly found it. Yeah, good. John did a good job there. So that's the correct in degree for each one. So in this algorithm, what we do is we choose a vertex with in degree 0. So as you can imagine, in the topological sort, we want the starting node to be the one with the degree 0. So in this case, I would be choosing A. And then what we do is we print that vertex A, and then remove that vertex, get rid of that, and all edges coming out of it. So get rid of these edges. And now we have a graph like BC and so on. Decrement the in degree of all the neighbors of the vertex by 1. So for example, B and C had in degree 1. So we will decrement them to by 1, so they become 0. Then repeat 2 to 5 until 2 through 5, or 2, 3, 4, 2, 3, 2 to 4, until all vertices are removed. So the next one, we're going to find a 1 with the in degree 0, which is B. And then what we do is we remove B, and then we reduce the in degree of connected vertices. Like, for example, D need to be reduced by 1, and E needs to be reduced by 1. Okay, and then we choose the next one, C, the in degree 0, and then remove the, you can reduce the in degree of all the vertices that are connected to C. So E will be reduced, oops, hold on 1 second here, 0, and F will be reduced to 0. So then you get D, then you get E, then you get F. Now, if you draw the link, there's a link from A to B, and A to C, and B to D, and B to E, and then there's a link from C to E, and C to F. So that's a topological sort. That seems a lot easier in some ways than what we did before with the DFS, because all we have to do is to maintain a table of in degrees and then process them as you go. Okay. So as an example, I would like you to complete this. Find a topological sort for this one. Maybe the nodes are 1, 2, 3, 4, 5, 6, and the in degree. Okay, so let's take like a few minutes to do that. If you have the topological order of 1, 2, 3, 4, 5, 6, you can type it in. They don't have to be unique. Okay, so you might have a different topological order than someone else. That's okay, as long as the conditions are satisfied. So in degree of 1 is 1, in degree of 2 is 2, in degree of 3 is 0, in degree of 4 is 2, in degree of 5 is 1, in degree of 6 is 2, and in degree of 6, wait, did something wrong here. In degree of 4 is 2, in degree of 5 is 2, in degree of 6 is 1. Okay. All right. So are you okay with this? Any questions? All right. So let's do the algorithm. We're going to start with 3. That's the one with the lowest in degree, right? So we start with 3. and then we reduce everyone connected to 3 by 1. So 4 and 1 are connected. So 4 will be reduced to 1, and 1 will be reduced to 0. So next we choose the next 0, which is 1, and we reduce anyone connected to 1 by so connected to 1, you can you have 4, 2, and 6 connected to 1. 4, 2, and 6 connected to 1. So 4 will go to 0, 2 will go to 1, and 6 will go to 0. And then you pick the next one from the list that's not been picked. Let's say we pick 4. And you reduce anyone connected to 4 by 1. And that's going to be 5. So this would be 1. And 2 will have to be reduced to 0. And so we get that. And then we pick 2. And so 2 connections, so we don't do anything. Then we pick 6. And then finally we pick 6 is not connected to anything. Finally we pick. So make sure the right thing, read all the links. So 3 has a link to 1 and 4. And 1 has a link to 4, 2, and 6. And we have 4 has links to 2 and 5. And then 2 has links to nothing. 5 has links to nothing. 6 has a link to 5. So we found the topological order, and that's how this is going to work, right? Okay. So let's ask some questions here. First of all, the complexity questions. Oops. Oh, 1 second here. Get that back. Okay, I'm going to come back just 1 second because I'm having trouble with the connection here. Okay, I have to unshare and reshare again. Stop sharing your screen. Okay, let me get. Okay, looks like we're back, at least coming back. Okay, it's lucky that we are not flying a plane or something, otherwise we'll be crashed and dead by now. Okay, yeah, so yeah, let's go through sort of implementation details here. So the implementation is essentially given this, and you have to maintain, you have to maintain a space, the size, because contain in degrees of nodes. Now, there's a question of how. So one of the things you have to do is that you have to compute all the in degrees, right? So in the algorithm, so to compute all the in degrees. So let's think about that. compute all the in degrees. Okay, how expensive is that? For example, if you store the graph as an adjacency list, just like that. Now, if I want to find the in degree of node, how much work do you have to do to find the in degree of a node? In other words, if I take a node like, let's say, 1, I have to find all the places where 1 is appearing, right? In degree means that there's a link coming to that node. So there could be a 1 here, 1 here. Okay. One, if you find these strings in the adjacency list, that right. So find the find the simple one node. Audio is choppy. Okay. Hello. Okay. Can you hear me? Okay. All right. So let's continue. Now, so to find the in degree, you have to go through this entire list, which is going to cost you v time, and then all the edges. So for each node, it's going to cost you n plus e work, but because node is going to cost this much work. Okay, because it's very difficult. It's still choppy. All right, I'm not really sure. Let me see what I can do. I'm not sure that I can do something about it, but let me try. Okay. So basically, I think to finding the in degree from an adjacency list is very expensive. Okay. Is it still choppy? Okay, it's better. All right. So let's do that. I'm not really sure why the audio is choppy, but hopefully, I mean, let's get through that. We have only a few minutes left. But if you had the adjacency matrix, finding the in degree is very simple. So, for example, if I want to find the in degree of a node V, all I have to do is to count how many ones are here, and that only costs me big of V to do that. Just have to go through that column. So sometimes if you store the matrix as an adjacency matrix, if you store the graph as an adjacency matrix, it's a lot cheaper to compute that. But if adjacency list, it saves you space, but it's very hard to compute in degree. Okay, so this is an expensive operation. So it would cost you this much work to do that. Ne plus En. Now, if you really think about it, E is of the order n squared. Okay, E is the number of edges, and the maximum you can have is n squared. Right. So if you really simplify this, you have n times E plus n squared. But if you think about E as order n squared, then you're looking at n cubed for the complexity for this findings. So it's very expensive to compute the in degree, especially if the list is an adjacency list. All right, and you can imagine that this will be very hard for something like Facebook, where you have 3 billion users. So n cubed would be 3 times 10 to the 9 to the power 3, which turn out to be 3 to the power 3, 27, times 10 to the power 27. So you're looking at 9 times 10 to the 27. And this is huge. And that number is very, very large and cannot be computed very easily. So one thing I think you're going to learn as you go through computer science is that there are limitations to what we can compute, especially when things become so big, like in the Facebook age. You have so many things that has become big. Okay, because the sound is not great, I'm going to stop here and let you guys ask questions on the chat.